Okay, my name is Amy Gallagher, and I am the Conference Manager for the Wearable Robotics Association, and I'd like to take this opportunity to thank you all for participating in today's webinar. I wanted to take a few minutes just to tell you a little bit about the association and our WearCon event. The association was created in 2015 as our team saw a need. There was not yet a forum established for those who are involved in the wearable robotics community. We wanted to create a place where they could all come together, and our goal in creating the association was creating this community that brings together entrepreneurs, businesses, and academics to collaborate, network, and share ideas, and I think we have done that. Thank you to those on this call who attended WearCon this past February. You're already members of the association. As you can see, there are several benefits of membership, including access to our many learning opportunities that we offer throughout the year, and there's also discounted WearCon registration fees, among others. Today's webinar is free to all attendees, but in the future it might be something that we will charge a fee for. And members will receive discounted or complimentary registration at events such as this. We're accepting members now, and you can contact me at info@wearablerobotics.com for more information. You can check out the website and the email address. They're both at the bottom of the slide. As you can see, we have several events coming up over the next few months. We offer monthly webinars, the next of which will be held on September 21st, where we'll profile a robotics company, currently free for members and non-members. We also offer in-person lunch and learn educational sessions within the United States. These sessions, they focus on a topic that's relevant to those involved with the wearable robotics community. In June, we held our first session at Harvard University in Boston, and the topic focused on cybersecurity and wearable robotics. Our next event will be held on October 4th at Exobionics in San Francisco, and we're planning a third event for January that will be held in Washington, D.C. The Lunch and Learn sessions are free for members, which is a great benefit, but there is a fee for non-members to attend, just another reason to join. And of course, we have WearCon 17 coming up April 19th to the 21st in Phoenix. WearCon is the only event focused on wearable robotics, and there are many ways to get involved. You can present a session, sponsor, exhibit, volunteer. We're in the planning stages for WearCon 17 right now, so if you have an interest in getting involved, now is the perfect opportunity. So visit the association website or feel free to contact me for more information on any of these opportunities. And now I'd like to turn the presentation over to our experts from Anybody Technology. Thank you.
Thanks, Amy, for the information about Wearable Robotics Association. So I think we take it from here, and we will mute your mic. Thanks very much again. Okay, I'd like to welcome everyone to this webinar that is a joint event by Wearable Robotics Association, or in short, WERA, and Anybody Technology. We appreciate your time and hope that by the end of this webinar, we have successfully introduced and discussed some concepts and techniques for in silico modeling and simulation of exoskeletons using Anybody modeling system. First, some technicalities for those of you who haven't used this webinar system before. On the right-hand side of your screen, you see a control panel. It can be collapsed or expanded by pushing the orange button. If you think of a question during the presentation, please don't wait until the end of the webinar. Just open the control panel and find the questions pane where you can write and submit questions immediately. Here we will try to answer as many questions as possible at the end of the presentation. However, if your question is not addressed due to the time restrictions, we will try to do so by email in a few days. Also, I'd like to let you know that this webinar is being recorded, and you will receive an email with a link to the recorded video of this webinar. So for this presentation, you will see an introduction to the antibody group and the antibody modeling system by me. My name is Mohammad Shourijeh. I am an R&D engineer at Antibody Technology. Then we will move to the main presentation, which will be mainly performed by Moonki Jung, who is a senior application engineer at the company, Antibody Technology. And finally, I will give you some final words, and right after that, we move forward to the Q&A session. Antibody group consists of the company, Antibody Technology, and the research groups. The company is based in Aalborg, Denmark, and provides licenses, training, support, as well as consulting services. Antibody Research Group includes the main research group at the Aalborg University run by Professor John Rasmussen, as well as two other groups, one in the US under supervision of Professor Petrella, and one in Germany by Professor Dendorfer. Antibody modeling system is the software that does multi-body kinematic and dynamic analysis of human-centered simulations. The software comes with the Antibody Managed Model Repository, or in short AMMR, which includes many application examples as well as open body model. AMMR is a collection of generic musculoskeletal models that are developed and contributed by researchers around the world. So essentially, if your application is one of those that are already in the AMMR, you just need to minimally change the model to be adapted to your data. Otherwise, you can start from those open body models and develop your own model with your desired entities. Anybody has somehow unique simulation features that I'd like to highlight. Man-machine interaction simulation using our user-friendly SolidWorks to Antibody import toolbox. The second one is the reaction force prediction tool. If there have been some external forces on the human subject, for example, that you couldn't measure for any reasons, anybody can predict those for you. This can be used, for example, for the forces at the straps of an exoskeleton that currently there are no cheap sensor or technology that can measure three-dimensional distributed forces at the straps. Also, you can do subject-specific morphing of the bones in anybody based on the medical images. Okay, this slide explains the principles of doing inverse dynamics in anybody briefly. This requires motion and external forces and moments as inputs to the model. Of course, as was mentioned earlier, anybody users have an option to predict the ground or in general reaction forces as well. Also, some kinematics can be decided and estimated by anybody, so you don't need to provide all the kinematic data. Then, using the muscle recruitment optimization solver with various options for the objective functions in the optimization, anybody calculates the internal musculo-skeletal variables like muscle forces, muscle activations, joint reaction forces, etc. If you have a detailed CAD model of a mechanism or a machine, one example is like gravity compensation mechanism for the exoskeletons. If you have one of those mechanisms, you can easily import them into anybody. SolidWorks parts and mates, so there are components in SolidWorks modeling which are called parts, which are basically segments, and the joints are mates. So those parts and mates will be automatically converted to rigid body segments and joints without any further effort. Subject-specific data such as anthropometrics and medical images will be used to scale the generic model that will join the CAD model and will be run for this specified activity of daily living. Anybody is capable of being interfaced with FEA, finite element analysis tools, for stress and strain analysis. Before doing And after any-body simulations, essentially you can use programming interface for more scripting, or for example, running an outer loop of optimization around any-body simulations. Okay, now I pass the mic to Moonki, who will present the exoskeletons and any-body.
Thank you, Mohammad. Now, I'm Moonki Jung, who is working as Senior Application Engineer in Antibody Technology. From now, you will see an illustrative example of exoskeleton inside antibody modeling system, and also you will listen what the intention of this model is. Here, we prepared an antibody exoskeleton example. Let's assume that there is an exoskeleton designer who is working on the conceptual design of exoskeleton. Then he may want to know in advance regarding how his exoskeleton design will affect its users. And there may be some followed-up questions. For instance, how should we attach an exoskeleton to the human? Or what are the affected human variables due to the use of this exoskeleton? In this model, we assumed that there will be 6 ideal actuators at some degrees of freedom, such as hip flexion, knee flexion, and ankle plantar flexion. And for each illustration, we assumed that there are 2 different types of actuators. One is strong torque actuator, and the other one is medium torque actuator. And we modeled some interactions between human and exoskeleton in form of a conceptual strap at pelvis, both thighs and both shanks. Physically, the interaction means that there are 6 degrees of freedom, forces, and moment between exoskeleton's part and the human segment. As aforementioned, you can define the motion of a human model in antibody modeling system by using various mathematical expressions. That is the way how we could implement the seat-to-stand motion using parameterized joint angle definitions without motion capture data input. Both left and right human models are doing the same motion. The only difference is that right human model is equipped with an exoskeleton. Also, as mentioned, antibody modeling system is based on inverse dynamics method, so we have several different modeling schemes in order to predict some unknown forces. So we have developed a method to predict the ground reaction forces using only kinematics information. In this kind of a human exoskeleton combined model, the ground reaction force prediction should also consider the mass properties of the exoskeleton model. Now you can figure out what kinds of outputs are available from antibody modeling system regarding human model. First, on the left-hand side graph, we can see how much knee flexion moment of muscles can be reduced by the assistance of the exoskeleton on the left-hand assistance of the exoskeleton. The red curve shows the knee flexion moment by human muscles when human does not use this exoskeleton. So it means that this curve can be regarded as a reference knee flexion moment. Then the gray curve shows the knee flexion moment by human muscles when human wears the exoskeleton with medium actuators. The efforts from human muscles could be reduced, as you can see here. Then this gold color curve shows the knee flexion moment by human muscles when human wears the exoskeleton with strong actuators. This is a kind of ideal case in order to check how much an ideal exoskeleton can reduce the human muscle effort. This right-hand side graph shows how the knee joint reaction forces could be reduced with different actuators as well. Then, exoskeleton designers also may want to determine the specification of the actuators in the exoskeletons. Left-hand side graph shows the torques of the knee actuators in the exoskeleton. The strong torque actuator and medium torque actuator will show different patterns each other. Also because we know the kinematics information of this entire model, including velocity, that we can calculate the power of the actuators as well. From this slide, you will see some different demonstration cases of exoskeletons using antibody modeling system. And there are several interesting topics, including metabolic energy cost evaluation, motion capture data use, interaction between human and exoskeleton, and conceptual soft exoskeleton model. Metabolic power seems to play an important role in the design and evaluation of exoskeletons. So this video shows how metabolic power will change according to the phases of box lifting motion. This model is developed by Dr. Mohammad, who was talking just before. And he tried to some what-if test in order to figure out which joint will be most effective to reduce the total metabolic power during the box lifting task. For simplicity, here we assumed that the constant amount of the assistive torque at each joint. But in reality, this torque pattern can be programmed in different ways, of course, as you want. Antibody technology has been involved in several European space agent projects with other partners, usually in Europe. One of our recent projects is to develop a countermeasure exercise device in space in order to make astronauts increase the ankle plantar flexion torque so that the muscles such as soleus and gastrocnemius will be more activated. In this model, we try to test how much ankle plantar flexion torque can be reached by these two different actuators. And also, we wanted to simulate the individual muscle activations as well as the interactions between the exoskeleton and the human. In this video, this human model is driven by motion capture marker data, and the ground reaction force is measured by force plates. Here we added a conceptual knee exoskeleton with zero mass so that it can only add some assistive torque at the left knee joint. So you can compare how the left and the right knee flexion moments of muscles can be different to each other. And here also you can see the actuator moment and its power as well, according to the different phases of gait. This is a conceptual model to demonstrate a kind of a soft exoskeleton. These black lines represent wires, and this green cylinder shows passive stiffness, which means a spring, whereas this red cylinder shows active actuator, which will only work when ankle plantar flexion will happen. The main purpose of this model is to test how the combination between active and passive actuator will be implemented in the simulation model. In antibody modeling system, the pattern of this actuator torque or force can be programmed based on the position and the velocity information of any kinematic measures. As a company which is located in Denmark, Anybody Technology is involved in several EU research projects. There is a project called MoveWeight, which is also related to exoskeleton research and development. And one of its aims is to support some task of industrial workers in the factories. So we used some motion capture data from our project partner Alstom, which is located in Spain, about their workers' tasks such as wire winding and sandblasting. And we tried to figure out the range of joint kinematics, including position, velocity, and acceleration. Also, we tried to figure out the range of joint torques for these tasks using the measure the force input and the ground reaction force prediction method, as you can see in these two videos. This is another example from the same MoveWeight EU project. Now we are working on the simulation of the conceptual passive exoskeleton model with gravity compensation mechanism in order to support the industrial task. I know that at the moment there are many researchers who are working on this kind of mechanism, so we hope that also we can make a good result compared for future opportunities. So this is another example of EU exoskeleton research project called Exosuit, and one of its partners, Wearable University, is using antibody modeling system for these simulations. Now I'll pass the mic to Dr. Mohammad again.
Thanks very much, Moonki, for the very interesting presentation. So these are just final remarks. So I'd like to briefly review the information that anybody can provide to an exoskeleton project. So at the design phase, I would say to find optimal parameters and variables of exoskeleton, like torques, powers, kinematics, stiffness in case of passive exoskeleton. And then we need to define some comfort or endurance analysis to be able to evaluate the exoskeleton. Those can be potentially joint loads, muscle activations, metabolics, or the interaction, distributed force and pressure, basically at the straps. And so we can categorize three phases that anybody can help the exoskeleton production. One is pre-prototyping. So basically, there's no actual prototype out, and there are only conceptual designs. So in that phase, we can import the CAD models into anybody and run simulations to evaluate those potentials for the prototypes. And then the second one is post-prototyping. So once the prototype is out, we need to evaluate the exoskeletons on different populations, for example, different people with different sizes and in different tasks and in different load cases. And also operational. So what would happen in terms of evaluation on individuals and what are the best adjustments in terms of optimality from the human-centered design point of view for the exoskeleton, and then the interaction between the exoskeleton and the human. Okay, so this is just a general slide that I'd like to show you. So if you'd like to see our previous webcast, please visit our YouTube channel. It's called Anybody Technology, and you can find the links on our website as well. IRS 2016 in South Korea, so Moonki and I will be there. If you are there, please come and meet with us. We'll be happy to discuss concepts about exoskeletons or any musculoskeletal modeling and simulation things. We will be also in Wearable 2016 in Spain. We will present, and also we will have a booth there. So please meet us there as well. And I encourage you to visit our website, anybodytech.com, for useful links. For example, if you'd like to see publication list. And if you have any questions, send an email to inquiry@anybodytech.com. Okay, it's now time for some questions. Actually, I see that I've received several or many questions. We're now trying to sort them and try to answer them one by one. Okay, so let me ask this one first, Moonki. Can the exoskeleton modeling be used with mocap AMMR? So I think we showed a slide on this.
Yes, it is. So there are some of our users who actually did the motion capture for the human with exoskeleton is equipped. So it means that they try to put the markers on both human and exoskeletons, so they could capture the full kinematics of both human and exoskeleton. And there are two ways of modeling the interaction between human and exoskeleton. So also some people try to measure some pressure between human and exoskeleton, and actually those pressure can be used as the input of the simulation for this inverse dynamics. But if you don't know those interactions, then also we can assume some forces are there, and also there is a way to predict those forces. So if you have the motion capture devices and the physical prototype, then yes, it's possible to use this simulation with motion capture data for exoskeleton.
Okay, thanks. There is another question. 6 degree of freedom forces and moments. Can you define a bit more, and why 6 degrees of freedom? I assume it's asking about the number of degrees of freedom between the exoskeleton and the human body. Can you comment on that, Moonki?
So basically, the mention why I mentioned 6 degree of freedom forces and moment between exoskeleton part and the human is that because theoretically that the 6 degrees of freedom is the maximum degrees of freedom between two segments, but also you can limit actually there are different ways in any modeling system to model these interactions. So you can just put 3 forces and 3 unknown forces and 3 unknown moments to predict, and instead you can define several different contact points and put individual unknown forces on those points. So I think we will contact you individually regarding some detailed information. But in our publication list, there are some papers about ground reaction force prediction. So I think that will be a good reference for your interest. Thanks.
Okay, thank you. There's another question. Do I need to know the joint angle trajectories to prescribe the motion for my model? For example, in the squat motion with the exoskeleton that you showed. I think we already answered that, but if you have more comments on it, please feel free.
Yeah, so what I showed in this model is that if you have your motion capture data, then also you can drive your model using the kinematics as well. But if you don't have the motion capture data, that actually you can model the sit to stand motion. So what I did in my example is that I thought that the deflection is the primary kinematics angle rather than the others. So I set the deflection angle as independent angle. Then there are some. You can set the other angles as dependent angles. But also, the one important thing is that the projection of your center of mass should be inside the support rectangle bit, which will be determined by the location of your foot. So also I put the projection of center of mass inside the boundary of a 2-foot area. So there are some assumptions that has been adopted to create this model. So also this model is open in our our wiki pages. So actually anyone can access and download this example freely. Thanks.
Okay, thank you. Here's another question. Is energy data captured from sort of oxygen meter or calculated in anybody simulation? So I think I can take this one. Yes, this was simulated. So we have an extensive metabolic power model. It's based on the model in the literature from Umberger et al. In 2003. So I think that's a famous metabolic energy model that is used by many researchers. And we've been working on it to make it better, actually. So we think there's room for improvement. But the results that we showed was basically exactly based on the model presented by Umberger et al. In 2003. Okay, there's another question for you, Moonki. You mentioned about human variability in the simulation model. Can you adjust for different body size and shape, or more default body size and simulation? I didn't understand the second part, but I think it's asking about, in general, about how the exoskeleton and the human, are those scaled together?
Yeah, so here we didn't explain too much about our human model itself because the topic is dedicated to exoskeleton. But yes, our human model is capable. We have the feature of scaling our human model based on the population percentage or some external length of the segment. So actually, you can make a big person or a smaller person by scaling our human model. Then you can test different size of the humans by changing our human model with different settings of your exoskeletons as well. And also, one thing what I want to say is that also actually, not only for the segmental length, also actually you can scale the muscle strength in our human model by, we have different muscle parameters that you can play with. Then also you can simulate a weak person who has weaker muscle strength. Then that will show you some different muscle activation pattern when human wears the exoskeleton. Thanks.
Okay, thank you. So there's another, I would say, rather general question. Is there a list of published papers of anybody? If so, where can I find it? So the list of publications can be found on our website, anybodytech.com. So I encourage you to go there. You can see a long list of publications since 15 or maybe 20 years ago. Let's go to the next question. You mentioned the term kinematic measure. Could you elaborate on what this means? I think I can take this one as well. So kinematic measure is the term that's used in multi-body kinematics or multi-body dynamics. So when you write the equations of motion, if you use absolute coordinates, or if you choose a set of coordinates that you have constraints, so the constraint equation, the left-hand side of constraint equations will be your kinematic measures in our system. So a kinematic measure is the left-hand side of a kinematic constraint. And let's go to another question. Okay, can you give more detail about the local modeling of the interface between the exo and outer surface of the limbs? So it's asking about the interaction. I think there was another question. It was asking about if the interaction is hard or soft. Can you elaborate on that?
Yeah, so basically we use a similar approach that some of our users have used for the ground reaction force prediction. So if there are multiple contact points between two segments, it means that that will be the statically indeterminate problem which cannot be solved in a unique way. So the way that we used is that we defined several contact points, and we defined several artificial muscles for all those contact points. It means that all those redundant unknown forces can be combined into one single muscle recruitment optimization problem with other real muscles, then we are solving all those unknowns in one problem with other muscles. That is the way how we model those interactions.
Okay, thank you. Here's another question. How do you propose to have a similar rate of torque at the knee and hip actuators all the time? So I think that really depends on the control strategy. So if you really, and beforehand, basically, you know, and you have that information that, you know, the rate of the torque between those two joints are somehow dependent, you can make a kinematic, or you can make a measure in anybody and basically relate those two variables together. However, if you don't, basically you need to leave it for the optimizer. So it really depends on the case and you know, the experimental or the scientific evidence that you have before the simulations. Okay, so I'm receiving more questions. Is it possible to model a different formula to measure metabolism rate? It means I have my own formula to measure metabolism rate. Is it possible to change the standard formula with my own modified formula? I would say that's possible, but that should be done outside or as a post-processing. So basically at each instant of time, at each time step of simulation, you receive all the outputs that you want, and those outputs will be used in your metabolic power model. The results that we showed was from a model that is implemented in C++, so that's in the source code of the software. But if you would like to implement your own, that should be through a scripting interface in Python, C++, or MATLAB. But somehow as an external source, as a tool or as a post-processing tool. Okay, so here's another question maybe for you, Moonki. Is there any other way besides SolidWorks to interact an exoskeleton with an antibody model?
So the most of the exoskeleton model that you could see in this presentation are actually from SolidWorks system. So we have our separate module, which is called SolidWorks to Anybody, which can translate SolidWorks assembly into corresponding NScript model. What you can do is that you can combine the Anybody human model and translate your exoskeleton model inside Anybody modeling system. Usually the remaining thing is to define the kinematic constraint between human and exoskeleton, and also you can define the interactions between human and exoskeleton as well. Then you can run the simulation with the combined human model. So that is the typical way that what I personally or some of our customers are using at the moment. Thanks.
Okay, thanks. Here's another question. How could I understand the benefits of using an exoskeleton? For example, if I want to perform a lifting task, what outputs should I compare with and without the exoskeletons? So I think I can take this one. So in the case, for example, that we showed, our target or the objective function, you can call it, or comfort endurance analysis. So the variables that you set as your targets, in that case was the metabolic energy or metabolic power. So that was our goal that we were after. So we tried to compare the two cases with and without the exoskeleton. And we saw that if we increase, for example, the hip joint, the torque assistant at the hip joint for this amount, the knee joint for this amount, and the ankle for this amount, this is the optimal case. And optimality is basically what we defined ourselves, which was the minimum metabolic power observed by the human while wearing the exoskeleton. So it really depends on the case and how you define the objective function. Okay. Maybe, yeah, there's like another general question. Are you selling a software package or service for development analysis? So I think we discussed this. So as a company, we sell license, training, and consultancy. We have a lot of also collaborations with companies and institutions for R&D projects. So we develop more, we do research more, but those are the main things that we do. So license, training, and consultancy. Okay, so I think I'm still receiving some questions, but maybe we stop just right here, and then what we're going to do, we're going to answer the questions that were left unanswered. So we're sorry that we couldn't answer all the questions. What we're going to do, as I said before, so we're going to send an email with detailed answers to your questions that were unanswered, and please feel free to send us an email back if you feel that you're not convinced or you need more discussion. And also, like I said, the recording of this webinar will be available in a few days, and you'll receive an email with a link to the recorded webinar. With this, I'd like to conclude and close the